You should actually post that, whatever post we got, because at my work, I've spent an obscene amount of time actually like writing R packages for this exact.
Oh, you have?
Stuff, like HTML to PDF, like slideshow stuff, which is
Oh yeah, there's.
hysterically arbitrary.
I there's online apps you could get to do it that weren't working. They all did the same thing. I was just printed the first page in a PDF. I couldn't get anything else to work. And then there's this. I'll post the code. I posted the code, stuck it in, it worked, and I didn't look at it. I was so tired. I just wanted it to work. I should never do this. I should just say I'm going to lecture from the HTML and not waste my time. But sometimes I just can't stop myself. So, all right. So it's a continuing lecture. Some of the early slides we've already seen. So I just gave you our markdown that goes with the previous PDF. And of course, you have another PDF to go with it too if you knit it, and this one will work. Didn't work. Never mind. No, this is the one. But at least I gave you the PDF. So again, this was our examples we did. I don't think there's anything new to show you for these ones because we went through it all before. Sometimes I cut off this part. So again, it gives you the variance terms. It gives you the fixed effects coefficients. These are the parameters. And then sometimes it puts the correlation down here. So anything here? No, just same stuff. I didn't go over this. So anyway, this is how you get the, you just take the model. If it's a likelihood-based model, you just put it in the AIC, it'll give you back the AIC. Right? You don't have to calculate it yourself. It'll also have this ICC command you can use. It gives you the interclass correlation coefficient, which will have a different interpretation based on the model. Typically, you just look at the adjusted. The unadjusted is typically not of interest. And I'm just showing here, I can also get it myself, this one, by doing it by hand. So again, this thing here, if you look at this part, I get the variance of one of them, I get the variance of the other term, I get the total variance at the bottom here. So this is just, what did I call it? This right here is just sigma squared 0 over sigma squared 0 over sigma squared E, which is ICC, which is just the correlation. So if I have different levels, I have 2 levels here, but if I have three levels, let's say, so house, individual, and repeated measure, I can get the ICC for different comparisons. Like typically in the denominator, you always have the total variance, which is the sum of the variances of those things. And the numerator, I can put the variance due to household, and that's one ICC, and the variance due to individual within household. I can get that one. You simply don't put the ICC is not defined for the error term. That's just everything else. So it depends on the model and how you can get back these things. You can always get it by hand by just grabbing these variance terms directly. That get variance residual is a way to get the residual variance. So this gives you back. This is sigma squared 0 estimate, and this is sigma squared E estimate. So I just get it back. Again, you can just run ICC and it does it, or I can do it this way. I can go back to the previous page and just see the numbers and type them in. So you can get it different ways. So that means, that would imply that the correlation in this particular case is very high, right? So it's after I condition on the X, people's repeated measures within the individual tend to be much closer than if I took a random 2 people and looked at them, right? 0.83 is the correlation, let's say residuals on one person's observation to their other observation. So if I took pairs of observations on subjects and correlated them, I get something like 0.83. It's very high.
So it'd be basically like cross-sectional almost.
Exactly. If I get 0, as the between variance goes to 0, it's always relative, right? So as this gets small relative to this, it goes more towards independence. Because these are all scale, based on scales. So but basically, or it goes to zero, there'll be, never zero exactly, but if it goes to zero, that implies independence.
This new report just does like kind of for fun, get an idea of what your data is. I guess like if you get this in an analysis, like what do you do with this information?
That's what I was just thinking that, before you asked me, like, why am I telling you this?
I mean, it's interesting.
Well, ICC is often reported, now, because oftentimes, okay, mixed models are, for once, in like, and social epi, mixed models are used all the time, because you have clusters of people, usually communities or something, you have individuals within, and they want to know, where's the source of the variance coming in? Is it really communities are different, or people are different within communities? So take out the longitudinal part, it's just cluster data, which you can always also fit mixed models for. So it's a standard thing to report the ICC. I was just thinking, like, how does it help me in this context here? I mean, it tells me that there's a lot of between person difference, and relatively speaking, not that much within. So I could infer that CD4 count is pretty stable within an individual, relatively speaking, to the lability, which is how it varies from time to time. Yeah, but it was a good question, because I was thinking, you know, what would you get out of this exactly? And it tells you how much new information. I mean, if I was doing power calculations, you always have to put in this if you have cluster data, because it tells you how, if I have a fixed numbers of clusters, let's say, and I want to sample to find out how many people I need per cluster, or how many repeated measures for a person, if the person's a cluster, this will factor in. And this tells me I don't gain a lot by adding more and more observations per person. Because if it was one, I get nothing, right? If it's one, you have something wrong. You don't need repeated measures. Or your machine didn't, you have input error, something's wrong if it's one. But as it gets higher, it just means I want more clusters. I don't get a lot, or more individuals, if individuals my cluster. I don't get a lot more information by taking repeated measures. That's what it implies. Now again, you'll have this, if it also sort of implies in this data, maybe there's nothing that's time dependent that really explains anything, right? Because if it's perfectly correlated, it means it didn't matter what changed in time, right? So it gives you some sense of how much within person variability you have. And of course, I'm trying to explain that within person variability, you wouldn't want the correlation to be super high. It just tells you there's not much to explain. So, I can bullshit through it at some level, but those could be useful things to know. And it's often something that's demanded. So if you're doing social epi, and doing mixed models, you always report the ICC. They expect to see it. So.
Alan, does it help inform you, like if you fit a mixed model person and you were interested in fitting a GE, would it inform you, like, I mean, you always want to use exchangeable, right? But would it inform you, like, oh, maybe you use one of those at all? Or no?
I mean, it means, particularly if I had unbalanced data, I want to use exchangeable.
Yeah.
Because independence can be a terrible fit.
Yeah.
But not really.
Okay.
Not really.
That was like 0. So do we do anything with that information?
We saw that. So I'm just gonna, and then this is our other example. Again, we have same basic stuff. You can see for this example, I mean, it's kind of artificial. The correlation's still high. ICC still. And again, I just did the same thing by hand. Don't worry about it. So it's the same data, same CD4 counts. It's different people potentially because I select and different observations per person. So it's coming from the same data. It's not surprising. It's kind of like 0.8. And this is just the GE for that. And of course, we couldn't identify that one. Over that. And here is the one where we have a, let's go to the next one. That's. In this case, we have our, the variance of the intercept, the variance of the slope term, the variance of that thing, and we have their correlation. You'll often see a negative, and that's because if I'm looking at various people's plots, and let's say there's some upper limit. That as the intercept gets higher, the slope tends to get lower. It's often the case that the intercept gets high, can only go down or stay flat. So it's negatively correlated. You often see this negative correlation between the random intercept and the random slope. That's why you don't want to assume independence. Oddly enough, in Stata, it defaults to independence assumption. You never want that. You always want to allow for correlation because it just makes more sense that these things would be related. At least it's worth starting with that as a model. Anyway, this gives me the whole joint distribution. I have the variance, marginal variance of each, and they have their correlation, meaning I can get their covariance. I could generate random samples of the beta 1i, beta 2i, and the beta 0i from a multivariate normal based on the variance covariance matrix that I could define by these three numbers here. So when I say that you can use this to generate new data, that's how you would do it, right? I get my coefficients. Let's say I wanted to simulate data from this based on the fit I got for this model. And I want to generate a sample size of 1,000. And again, for now, there's additional complexity. Let's just assume the x's you get are sort of independent. They're not related to anything in the past. So in order to do this, I want to simulate it for a new population, I would generate a B0i and B2i for, let's say, 1,000 people from a multivariate normal with these variances and a covariance defined by this and the two variances. So now I'd have a different slope and intercept for every person. I'd have an error term right here. So here's the error residual. I generate random observations for every observation. Now let's say it's 10 per people. So now I have a data set of 10,000 where the first 10 rows are for person 1, the second 10 rows are person 2, all the way down to 1,000 or 10,000. I would take a random set of covariates. In this case, just think of it as time-dependent covariates. Don't worry about time-dependent, because that adds a whole other complication. So I just grab their sample of independent covariates, and now I have, I've got the fixed effects. I put that all together, and I can generate random outcomes from that distribution. That'll have the joint distribution implied by this model. Like we couldn't do that GE, right? Because we didn't make. First of all, there wasn't any assumptions about the error distribution at all. We only got standard errors for coefficients. We didn't get all the components you need to simulate a random sample. And so that's a good, important way to think about the difference. GE is not trying to estimate the whole likelihood, so I can't take the resulting fit of likelihood and actually generate data from it. I can only maybe predict a mean value given the covariates. Anyway, you could, in theory, take this and simulate new data based on this distribution fit. So it turns out, in this case, there's not a single,
Yeah, so thinking about data simulation, for example, I believe, let's say that I'm interested in antibody dynamics.
Sure.
Right?
Who isn't?
Yeah. And then I generate a simulated model in which antibodies are decaying, right?
Okay.
Over time at a specific rate.
So time, you have a time variable.
Yes,
it's
I
your
have.
explanatory variable.
Yes, exactly. So I have time, I have a set of covariants, and my outcome of interest is antibody titers
Yeah.
over time, right?
Got it.
So then I assume decaying of the antibodies, right? And I
Well, no,
assume-
I'm assuming you're gonna fit a model to it first.
Yeah, so, yes, okay.
You're gonna assume some model and fit it. And let's
Yes.
say it has a random intercept, a random slope per person.
Yes.
Let's assume that.
Yes, and then I want to know if on a specific, different population, the antibody is also decaying. Is there a way to compare what I observe versus this model to see if they are actually decaying? You know what I mean? I don't know if
Yeah.
that makes sense.
In other words, you wanna say, I have a whole new population. I wanna know how well this fit to this data fits that population?
Like, yeah, exactly. Being that if they are decaying, then I will see no difference between what I am seeing here in this model.
I mean, to me, that's more like, what would you do? It's not so much related to this, but what you do in practice, I think, is you'd have, pull your data, right? You'd have a variable now that indicated population 1 and population 2,
Mhm.
right? And then, or like indicator that you're in population 2, let's say. So 1 if you're in 2 and 0 if you're in 1.
Mhm, mhm.
Then you would just have your, whatever explanatory variables, you have an interaction with that and the study population, and you've looked at those interaction terms to see,
Okay.
is it changing? But you could also do things like there is a way to fit models where you say, I want to allow the variance, let's say, of my slope term to be different between two populations. That's actually interesting. I should probably go over that in class a little bit. So you can stratify the estimates of these variance parameters based on other things. You can make them a function of one of the x's, right?
Okay. Okay.
So you could test that. Are they more stable here?
Yeah,
About
exactly.
the same, or are these ones more variable? That would be a possible test. Are the variance terms the same?
Yes. But then the right approach would be to feed a model that has an interaction term. The
So we just
population
fit
is
all
interaction.
data. I'd have a study ID, I'd be a population indicator.
Then
I'd
it's
have
an
that times, I'd have that as a main effect as an interaction with time, right?
Yeah, okay.
And you could have the other random stuff in there too, random coefficients and stuff. But I mean, your test of whether, the test of the interaction of time, and that tells you, is the average slope the same in the two populations?
Good.
But it doesn't tell you about the whole distribution, right? That's a different test. That would be like I can test the variance in one being different from the variance in the other of the random slope. I haven't taught you how to do that yet. So like how do I get variance components that are different in the two groups when I fit this? So you get variance components that are stratified essentially. And I'm going to look at that. That's because I know can do it and I haven't. Let me just put that here. Yeah, that's one of those bells and whistles. You know, you can add a ton of them to this stuff, but that's one that might be useful. Yeah, good question. For here, yeah, no. Do I have code with that? Here's a guy. AIC, you can just add a bunch of models. You know, if they're all the same data, right? They have to be on the same data. One thing you have to be careful with AIC, if I comparing the AIC and I have like different fixed effects in there and some of them are missing, this new covariate I'm adding to one model, not the other, the likelihoods aren't comparable. They have to have exact same number of non-missing observations. So always be careful for likelihood ratio tests or comparing AICs that the actual observations used to get the estimates are the same, because otherwise you can't compare them. The more data you have, since your likelihood is a product of all these probabilities, the more probabilities they are, the smaller it's going to get, right? So it's not comparable. Okay.
Sorry. Just
Yeah, absolutely.
If I understood.
Yeah.
So what I understood is that making sure that when you are adding more variables to another model, those variables have the same number of observations,
Yeah.
meaning the same number of missing data or.
Exactly.
Yeah, okay.
So I mean, we haven't talked about anything where that would matter because we're only talked about varying the random effects. We haven't talked about changing the coefficients, but AIC is more general. You can use it to compare like a model with 20 coefficients, 20 covariates versus 10 covariates. And a mistake that's often made is for the 20 covariates, maybe some of those are missing observations. So it automatically, whenever you do this, well, you have to put a certain command in, but typically it does complete case. So it only does the analysis on non-missing observations. I mean, it'll be a different number. And I think it would give you a warning, because AIC is just using the whole object and can see that, but just to be aware that that's a common mistake. People compare them and say, oh, the AIC is better here, but in fact, you just have fewer observations for this one.
Mhm.
Yeah. We saw that. Okay. You know, I'm going to give you an early spring break. Spring break. So, because we have plenty of time to go over what we need to go. So have a great spring break. Have a good lab today, and I'll see you. I'll see you a week from Tuesday. I may have to do I'll be at a conference, so I'll probably do a recorded or a live, but Zoom lecture. But I'll let you know. Okay. Thanks, everyone. Thank you.